Hi, welcome back. This episode I'm going to look at circular motion and the force that causes an object to travel in a circular path. I'm going to look at some simple examples, everyday examples. For example, a car travelling at 10 metres per second east as it rounds a corner and ends up with a final velocity of 10 metres per second south. Now, the magnitude of its speed has remained the same. It's been 10 metres per second the whole way, but because its direction has changed, its velocity has changed. And we say that the change in velocity is the final velocity take the initial. And if you remember when we looked at manipulating vectors, when you subtract one vector from another, it's the same as adding the opposite. So if I want the opposite of the initial velocity, I just rotate that 10 metres per second east and do 10 metres per second west. Now I can simply add the two vectors together by drawing them head to tail and then draw in the resultant vector. Once I've done that, that resultant vector is representing the change in velocity, the final take the initial. And also I know that acceleration is the rate of change of velocity. And if I show that acceleration on the diagram now of the car, I can see that the car has accelerated toward the centre of the curve. If that acceleration was to stay always at right angle to the direction of the velocity, that car would travel in a circle. Now, Isaac Newton came up with quite a few ideas on motion, and one of them was that if an object's motion changes, then something must have forced it to change, and that force must be in the direction of the change. That thought is summarised in his second law, which says F equals ma, or the magnitude of the force is equivalent to the size of the mass and acceleration, the product of the size of the mass and the acceleration. We know that acceleration is the rate of change of velocity, and when we look at circular motion, it is also calculated by the magnitude of the velocity squared divided by the radius. Newton's second law says that F equals ma, so if we substitute in for a, the acceleration in a circular motion, we get that the force that causes it to travel in a circle is mv squared on r. Now that force that's causing it to travel in a circle is acting in exactly the same direction as the acceleration, and it causes the acceleration, and it's called a centripetal acceleration, and the force which is causing it is called the centripetal force. Now you've probably heard of some other force which sounds similar to that, centrifugal or centrifugal force. I'll tell you now, that force does not exist. That's just an imaginary force. You often hear of people saying, if they're travelling in a bus, they're being thrown out as the bus rounds a corner. There is no force, as you can see, there is no force acting outwards. Most people think there is. The reason for that is they're in a different frame of reference, and I'll show you what I mean. With this car, imagine that there was an orange on the dashboard. As you're driving along in the car and you're rounding the corner, it appears to you as an occupant of the car that the orange is being forced out across the dash. It is not. As you can see by the dotted path, it is travelling in a straight line. In fact, it's experiencing no force. Its inertia is making it travel in a straight line. It doesn't experience a force until this point, shown in the diagram, where the pillar at the end of the dash starts to force it inward and make it follow the circular path as well. So this supposed centrifugal or centrifugal force, the one that is supposedly throwing you outward, does not exist. It is inertia, but from your frame of reference it looks like objects are being thrown outward. I'll give you another example. You've got a rock being rotated on a string. Now, what is causing that rock to travel in a circular path? What it is the force of the string constantly pulling it in. Without that string there pulling it in, that rock would not travel in a circular path. In fact, if the string disappeared, the rock would travel in a straight line. So the only force which causes circular motion is an inward force, a centripetal force. The centrifugal force does not exist. Now, you may have been on a fairground ride such as this, the Gravitron. And in this ride, it's a cylindrical room which rotates quite fast, and you feel like you're being thrown out and pushed up against the walls. In fact, you're not. The walls are pushing you inward. If those walls were to disappear all of a sudden, and that inward force was no longer there, you would continue to travel in a straight line. Now, why does it feel that you're being pushed out? Because the wall is pushing against your back, you feel like you are pushing out against the wall. In fact, remember that it is the wall pushing in against you. Now, I know a lot of you, it's just not intuitive and it just doesn't seem to make sense. It does feel like the wall's pushing against you, or if you see someone vomit in one of these gravitrons, it sort of flies back against their face and all that sort of thing. It's not. It's actually travelling in a straight line and you're coming around to meet it. I know that these idiots in this video I've got here probably won't accept that there is no centrifugal force either. What they've done is they've put their motorbike wheel against the roundabout in a playground and started spinning around very fast, and it looks like the two little girls inside the roundabout are getting thrown out. They're not being thrown out, it's that the inward force holding them in the circular path has been removed, and therefore they're continuing in a straight line. Don't try that one yourself.